This simple configuration is called a voltage follower or a unity buffer. And I'm saying it's simple because the output is simply connected to the inverting input and the input source is directly connected to the non-inverting input. And if we do the analysis just to see what's the value of the output in terms of the input, well, we know that the IP is 0, we know that the IN is 0, and what else do we know? Well, VP in this particular case is just simply VI, and of course VN and VP should be the same, so this is also VI, but the VN is the same as the V output, so that tells me that this is just simply the input. And that's basically why it's called a voltage follower, because whatever happens at the input will be reflected at the output. I mean, you might be wondering, do I really need a circuit? Do I need to use an operational amplifier and use power to like consume power just to get an output to be exactly the same as the input? And you'll be right to think this, but it has an application, and that application is to isolate a couple of circuits. So let me just explain this with an example. So in this example, what I have done is I replaced some sort of a circuit in here with its Thevenin equivalent, and I connected it to a load directly. No voltage follower whatsoever. And in here, I will be doing the same thing. So I took a circuit, I replaced it by its Thevenin equivalent, okay, and then I connected it to a load. But now what I've done is I separated it, or I isolated it using some sort of a voltage follower in here. So of course you should know by now, or you should know that this voltage in here will be the same as voltage in here. All right, so let me just put some numbers just to convince you that that voltage follower is actually important. So I will assume that that VThevenin, for the sake of simplicity, I'm going to assume that this is simply 1 volt, and I will assume that this circuit has an R Thevenin equivalent. This is what we call an high output impedance, okay? And why am I calling it high output? Because I'm assuming it's 1 mega ohm. And just as a quick reminder, a mega ohm is just simply 10 to the power 6 ohms. So this is a high output impedance, okay? So it's a very high output, and what we call it like output impedance because the output of a circuit in here, that's why it's the R Thevenin. Anyway, it's a high impedance, or impedance is just a fancy word for resistance, and it's resistance for AC circuits. But anyway, let's assume that it's a high resistance outputs, or high output resistance circuit or source. All right, and what we will do is I'll connect it to a simple load, and that load happened to be 1 kilo ohm. And just as a reminder, a kilo ohm is just 10 to the power 3 ohms. So let's try to figure out what VL is in this particular case. So VL, well, you can tell me I'm going to apply voltage division, and that gives me 1 times, well, the voltage I'm interested in is the 10 across the 1 kilo ohm resistor, so 10 to the power 3 divided by 10 to the power 3 plus 10 to the power 6, and that will give you 0.99 millivolt. So it's a fraction of the input voltage. So the input voltage happened to be 1, and what I got is not even 1 millivolt, it's even less than a millivolt. All right, let's do the same type of analysis using the voltage follower. So I will put the same 1 volt in here, the same 10 to the power 6 ohms, or 1 mega ohm, if you may. And then what I will do is I'll connect the same exact load, and that's basically a low impedance load, and that happened to be just simply 1 kilo ohm, or just simply 10 to the power 3 ohms. And let's try to figure out what VL is. Well, we know that VL is the output voltage of the voltage follower, so this one here is the same. So what we need to figure out the voltage at this particular point, and it will be the same as the VL. Okay. Now, the assumption is this current in here, which is IP, is just simply 0. If that's the case, there's actually no voltage drop across the R Thevenin in here, because the current across it is 0, which means that the voltage in here is the same as the voltage before it, which is just simply VThevenin. And VThevenin happened to be 1 volt, so that means here this VL is also 1 volt in here. So what happens now in this particular case is VL happen to be exactly 1 volt. So here's the point of using that voltage follower, or what we call sometimes a unity buffer, because the input is exactly the same as the output, so it's just a buffer. So what I've done is I have one circuit in here, this is this part, and in this circuit is what we call a high output impedance source. Okay, so that's a source circuit. It's called a high impedance or high resistance, high output resistance. Okay, and what we did is we connected it to another load, and that load happened to be a low impedance load or a low resistance load. Okay, so the voltage follower did its job by isolating the two circuits from each other, and in this particular case the loading effect that we've seen in here is not seen in the other part, and that's why we use voltage followers.